Good afternoon. Um, I'm very pleased to introduce the speaker of this seminar of the Rome Joint Astrophysics Colloquium, Professor Felix Aharonian from Dublin Institute of Advanced Studies and Max Planck Institute for Nuclear Physics in Heidelberg. A very brief introduction of his outstanding scientific career. He is one of the most eminent experts in the field of high-energy astrophysics and cosmic ray acceleration theory. And his theoretical research has been crucial in advancing the understanding of particle acceleration and diffusion mechanism, high-energy and neutrino astronomy, and in general, non-thermal phenomena in astrophysical sources. His recent studies are about extreme particle acceleration sites in our galaxy. And his research was also focused on the development of stereoscopic approach for the detection of gamma rays using imaging atmospheric telescope arrays, and on the advancement in the current generation of wide field observatories using direct detection of air showers from incoming gamma rays and cosmic rays. The title of his seminar is Cosmic Pevatrons in Milky Way. And of course, at the end of the talk, we will have time for some questions and comments, both from the audience in this room and also from our colleagues connected with Zoom. So I now leave the floor to the speaker, and thank you.
Okay, thank you very much, Giovanni, for introduction. I'm, of course, very happy to give a talk here. I don't remember exact how many years ago, but I gave a talk maybe 15 years ago here. And that time was quite exciting time when he started to release their results. And the main topic probably was, I don't remember exactly, but that was how could be so many tevatrons in the universe, in the galaxy and in extragalactic sources. And I'm going to talk about the next step. It's very unexpected. So talk about how could be so many pevatrons in our galaxy. I'll talk about that a bit later to be clear. So all gamma ray sources with spectra extending beyond 100 TeV could be pevatrons. We can call pevatrons because in order to produce gamma rays with energy more than 100 TeV in any realistic gamma ray production process, either protons or electrons should have energy at least 1 PeV. So that was we called ultra energy gamma rays with energy more than 100 TeV. These are pevatrons. So this is one. Second comment is that the gamma ray sources themselves, they are not still pevatrons. They are just gamma ray emitters. The accelerator could be located not exactly inside the emitter. Emitter could be surrounding accelerator or some giant molecular cloud could produce gamma rays. So, but it's clear, what is clear, they should be around or nearby these sources should be pevatrons, accelerators producing PV particles. So that is just very general comment. And since it doesn't work, even I'm pushing the right one. So I should continue or it could work? Yes, now it works. So just, I'm not sure I'll finish to tell you everything what I'd like to tell because there are very recent developments, just to kind of start with the summary of my talk, just to understand what I'm going to talk here. So we already know there are there's a great progress in astrophysics of cosmic rays, and but the particles produced with energy 10 to 15 EV or PV in our galaxy and 10 to 20 EV outside our galaxy, the origin remains uncertain. Generally, many things are uncertain with cosmic rays, but especially these two aspects. in order to, why is so much interest to these energies? Because not they are the highest energies, but in order to get particles accelerate to such energies, you need extreme accelerators. Extreme accelerators is not a simple emotional word saying they are extreme. Extreme means just everything is happening at the margin of theoretical expectations. So everything should be at the very margin. I mean, this is no compromise. So I'll talk a bit about that. So that makes this objects very interesting. Coming to the galactic cosmic rays, which is the topic of this talk, the challenge is linked so-called pevatrons. I started with saying what are pevatrons, and until recently, the question has been reduced to the issue to the question like, can supernova remnants accelerate cosmic rays to PV energies? So many of us were sure that it should be the case because supernova remnants are obvious candidates to accelerate particles in our galaxy, including highest energies. So how we should find these accelerators, maybe some years ago, no one of us could even tell how you can do that. It could be more theoretical, phenomenological aspect of the field because detecting, finding the pevatrons was a kind of dream. I mean, almost impossible, but nothing what happened. We've arrived the LASO is a mega Chinese project of gamma rays and cosmic rays. And this completely changed the status of the field. Now we have the catalog of pevatrons consisting of tens of sources, and numbers will increase, of course, with time. Now, I said about the first, the most important issue we thought before was can supernova rays accelerate cosmic rays? Now, to a surprise of many of us, it appeared that there are now a lot of doubts that supernova rays can do this job. And instead, we found that there is no clear candidate for pevatrons associated with supernova remnants. But what we know now that there are pevatrons clearly associated with massive stellar clusters. These are proton pevatrons. There are pevatrons associated with pulsar nebulae. This is about electron pevatrons, which, by the way, is much more difficult to accelerate electrons than not accelerate to reach the energy of 1 PV because they have losses, synchrotron loss of electrons. Nevertheless, we do have them. And the most famous one is Crab Nebula, and very, very recent microquasar. So that was actually is in archive. I learned just today. Could find in archive about the paper of LASO, including 5 microquasars accelerated particles to PV energies. So that was that I'll just try to cover in this talk. I was talking about the origin of the cosmic rays, and that typically for cosmic ray physicists, origin of the cosmic rays is reduced to identification or to finding the main contributors to the locally observed cosmic rays. So this is a very important issue, but not much exciting. I mean, because you could get some local sources, accelerators, which contribute, but not all of them. So field is much, much broader than simply origin, the count, which sources contribute to the local cosmic ray flux. So it goes much beyond of that. So first of all, cosmic rays, we call cosmic rays all relativistic particles, but it could be much broader. So in fact, the cosmic rays are so-called for substance of including the matter, radiation, and magnetic field is the fourth constant. So now, how we find them? Since they are the charged particles, it's not, we cannot just follow the tracks and then to localize the sources, we need some neutral particles which bring this information to us. So these are, of course, should be neutral, stable particles. And we know 3 of these type particles, photons, neutrinos, probably even gravitational waves in one way or another. Maybe we not directly are a result of cosmic ray interactions, but they could be connected to these accelerators, like in GRB sources. And so gamma rays, which we call photons, or photons we call gamma rays, is the basis of the gamma ray astronomy, and which the main hope is related to gamma ray astronomy, which should allow us to reveal these accelerators in our galaxy, basically in the universe. But we are talking about ultra-high energy gamma rays, then unfortunately, universe is opaque for ultra energy gamma rays. Entire universe, we could see gamma rays with 100 TeV energy, more than 100 TeV, only in the nearby universe, something like 100 to 100 megaparsecs. And 1 PV photons, mean free path is just simply 8 kiloparsec. It is because of interaction of gamma rays with 2.7 K background radiation, which gives you this limit. So that is the reason why I'm talking today only about the Milky Way, because we don't have this information from outside our galaxy. Okay, so gamma rays astronomy is considered a branch of astroparticle physics, but of course this is it's a discipline in its own way, which we often say is, provides crucial window to electromagnetic spectrum and is considered like the last window. The so-called last window actually covers 10 decades from hard X-rays like 100 kV to 1 PV, so it's 10 to 5 to 10 to 15. The so-called last window, 10 decades. While, for example, optical astronomy deals with half decade, something like 300 nanometer to 800 nanometer or 1000 nanometer. So that just, so you see indicated here. This is the half decade. Anyway, so this is only the question is just not gamma rays are produced. They cover, they are much more energetic than optical photons, but they cover many decades. It means physics could be quite different. It could be much more complex, much more rich with different type of process. And that is a general statement. But now what we see, surprisingly, we see all these energy bands from 10 to 5, 10 to 10 to 15 is detected, and with very amazing results in the region 10 to 15, which, as I said, was not even dream. No one could believe that it could happen one day, detecting all these particles. And the reason is not only LHAASO. LHAASO is simply the instrument, is a right instrument with right sensitivity, but also just how it could organized. I mean, these accelerators, these extreme accelerators, that is a very exciting news, and that will take years, if not decades, to try to understand how they can operate. Now, I should go fast, but maybe just say this last window, as I said, covers 10 decades. Experimentally, we get information about low or rays from MEV to GV of satellite instruments, very high, or TV photons we get from the imaging chunk of telescope. Basically, it's 0.1, 100 TeV, and ultra high energy or TeV particles is a very recent, last few years, and now the window is open in ABV, GV, TeV, PV bands. Low energy, high energy astronomy is provided by space-based instruments, and very high and ultra energy domain by ground-based instruments. So this is now what we have after several decades of struggles and controversial claims that if you probably don't know the history, it was extremely controversial with a lot of mistakes, misleading results, and somehow even the field was at the edge of catastrophe, just top to no investment. But fortunately, the first sources have been reliably detected, some 30 years ago, and that boosted the field. And with new Cherenkov telescopes, and now also with ground based arrays. So we have now more 300 sources, more than 300, and with almost 2,000 of astronomical source populations. So this is really exciting because 300 for astronomers is not a large number. It's just cannot be compared with X-ray astronomy or radio astronomy or optical, but what is interesting, all these 300 sources represent more than 20 source populations. So that was somehow in completely different environment. Astronomical particles can be accelerated, and not simply accelerated to energies, which is the age of the, which allowed by theory. Theory, I mean just the basic theory, quantum, the classical electrodynamics or hydrodynamics. So it's really amazing. It's not simply one PV is a very large energy. It's just theoretically, it's very, very difficult to explain. Now, I mentioned at the beginning that when I was 50 years ago, I was also giving talk here, but all we are very excited with the results of Cherenkov telescopes, and there was a TV sources, and it was a big surprise that universe is full of tevatrons. And now surprise continues, even more than surprise. So now we see that the galaxy is full of tevatrons. So before it was, I was saying about universe, because you could detect TV gamma rays from cosmological distances, while PV is very, very limited range. So now just show, this is often we use this kind of nice cartoons, nice figures, but it's not just simply nice. From all these images shown here, gamma rays have been detected. So that was when I said this more than 20, just only the sources related to neutron stars. There are several types of gamma ray sources, including the pulsars, pulse of winds, maybe, certainly pulse of in nebulae. I did show that there's another one, pulse of halos, and then millisecond pulsars, binary pulsars, and even the short gamma ray GRBs, which are related neutron star, the mergers. So you see more than 5, 6 type of sources, completely different type of sources related to only neutron stars. So that was, I think, is no need to repeat that, is very exciting. Now, so just a few words about the imaging Cherenkov telescope arrays. They are very famous instruments which have a huge potential with quite modest instruments. It's more than square kilometer, just to compare with space telescopes, which are less than 1 square meter. Of course, we are talking about different energy bands, TV against GV, pre-order of magnitude difference, but even that, the fluxes, the reduction of the flux is fully compensated. And you have 1 part minutes, the good energy resolution, the relatively large field of view, 5 to 10 degrees, because of the good sensitivity. You could do surveys even with such, of course, for optical astronomers. That is a very, very, very nice field of view. Okay, just there are different type of Cherenkov telescopes. What is the prototype of all arrays now we have, including CTA, was the Hydra, which did very nice discoveries. In fact, it somehow is not appreciated much, but of course, supernova remnants, Cassiopeia A has been detected by Hydra, M87 has been detected by Hydra, and Hydra also detected 80 TV gamma rays from Crab Nebula. So that was very interesting. I'll come to that. Now we have the largest array. This is the HESS. But what is going on now is Astra is coming, focusing on multi-TV gamma rays. And at low energy part, we have the first so-called prototypes, or actually not prototype, LSTC so-called in Palma, which start at low energy. So, and then I said, why these instruments are unique? Because you have the huge collection, even tiny fluxes, combined with even tiny flux gives you a lot of photo statistics. A lot of photo statistics with good angular resolution gives you good morphology. A good photon statistic combined with good angular energy resolution give you good spectrometry, and good statistics gives you generally timing. So these are instruments are multifunctional. They are very good for timing. They are good very for imaging. I mean morphology. They are very good for timing studies. And I just put here. I'm using this plot already more than maybe 15 years. That when first results we got, that to demonstrate how we could get this image. Is the image in TV gamma rays, not in other wavelengths. I mean, this first image, when you see the shell in gamma rays, so it proves that cosmic ray accelerated in the shell of young supernova remnants. And you could see morphology, a spectrum which has a very small error bars to tens of TV. And there's amazing timing, I mean, information we've has detected during the flare of blazar called PKS 2155. It found a 3-minute variability, which is not simply short. It is 10 times shorter than rotation radius of the black hole over the sea. We know the mass of this black hole. So this is, there are ways to overcome this. How could be smaller size than the rotation radius? There are ways, but this is not a trivial issue. But what I want to say, not to go to the astrophysics, just saying that you see everything is here with the same instruments, and also including astrophysics, the astronomy, galactic astronomy, and cosmology. With this data, you could actually measure the magnetic field, EBL, etc. So now this is not a topic of my talk. Actually, just I want to say that how is nice instrument we had, and result when you have a very sensitive instrument, then you will have a result. It's not guaranteed, of course, because beforehand no one could predict that so many type of sources could observe particles, TV energies. Now I'm coming to my main part of my talk, that is the pevatrons now, even not simply 3 orders of magnitude high energies, but if there's a problem to accelerate particles to TV energies, you could imagine how it would be difficult to accelerate particles to PV energies. Now, it was possible because of this Chinese mega project, which was original for cosmic rays, but there are a lot of muon detectors. I mean, you could see here the number of underground is not very deep, of course, but still muon detectors. You see the number of muon detectors, more than 1,000, each of them about 36 square meter. So that is and then a lot of scintillators. You could see how many scintillators. And in addition, Lahas was another instrument. It's called water Cherenkov detector, which is, you have probably this interesting, exciting results from the whole. This instrument is 3-4 times larger than Hawk and operating in a right regime, Hawk at highest energies, which is not so good for low fluxes, but it works at 1 to 10 TeV. And this is a very nice attachment to the huge, this kilometer square instrument. So I'm going to talk about this recent results of this instrument. So sensitivity, look at what is the sensitivity. Just about 100 TeV. It goes for 1 year, it goes several times 10⁻13. If you observe 10 years, then you get 10⁻14. This is very impressive even for advanced astronomical disciplines like X-ray astronomy. Moreover, the angular resolution of the source is only 0.25 degree. And so if you take 0.25 degree sources, if they are extended sources, this beautiful Chandra or Hubble sensitivities will not like 10 minus 16, 10 minus 17, will be go down to 10 minus 12. So to some extent, these instruments for extended sources are even more sensitive than so in fact, this is more sensitive in energy flux, of course. And another amazing thing, as I said, this was huge, but it's also because the muons, it has a potential to reduce the cosmic ray bulk. Because A showers produced by cosmic rays are similar to gamma ray showers produced by, initiated by gamma rays, but there are some differences. One of them is the number of muons. In gamma ray induced showers should be much less muons, 10 times than photon showers. So if you could measure the number of the muons, then you could reject this, take them as a gamma initiated events and reject. So background rejections. In satellites, you have the anti-coincidence shield, which reduces rays, but here we don't have such a shield, but we have these two muon pole showers. And in gamma rays, TV energies, this is a images. I mean, the shape of the gamma ray images. Anyway, so this is an incredible, so this is the cosmic rays. After rejection, you come here. It's about 300 TV. So 5 order of magnitude. So this is the, now fluxes are small, but we have a rejection here up to 1.3. And so we have a good still reasonable statistics. We don't have background. And the Lhasa is extremely sensitive to small brightness sources. That is maybe a record instrument, not in gamma rays, I mean in astronomy in general, because sometimes there is no background. And you'll see some figures. I'll show how you detect gamma rays individually. So this is very impressive sensitivity. Just to compare with CTA, these days all are talking about CTA. This Lhasa sensitive for 1 year. This CTA sensitive for 50 hours. So it's typical time to observe 1 year, and the Lhasa is 1 year. You see, huge difference. And also, this is a bit unfair figure because Lhasa, the angular resolution is much worse than CTA angular resolution. This is for point-like sources. So this is much more sensitive. It does mean you'll see that CTA has a great role to improve all these results, and in a different way. But we should keep in mind that beyond 100 TV, CTA will be not as sensitive unless we deal with flares. So this is the first result, absolutely unexpected result. It arrived during the COVID, actually, just first report I remember was just 1 week before COVID when was announced the first Lhasa collaboration meeting about detection of few sources. And then it grew some during 1 year. This was a paper published by Lhasa in 2021. It was, how many, I don't know, 12 gamma ray sources. And the condition was very tough to have gamma ray a signal above 100 TV more than 7 sigma. Anyway, the 7 sigma was arbitrary because it was 5 sigma, but during preparation of the paper, new data coming, so was much further time, so immediately it jumped to 7 sigma. It's very solid, unusual for gamma ray astronomy, in fact. And now you can see this is the Hess survey of galactic plane, and here you could see Lhasa sources up here. So that was clear above 100 TV that, as I said, the Milky Way is full of pevatrons. Pevatrons means indicator these pevatrons are gamma ray sources with energy more than 100 TV. Now, well, I just start with this. I want to say, actually, what means pevatron? It's the Tevatron is just like analogy of the Tevatron in Fermilab. So that was absolutely gets to 1 PV protons or electrons. But we are detecting gamma rays, so for sure, all gamma rays detected with energy more than 100 TeV are a result of interaction of particles observed in these pevatrons. So you say 100 TeV gamma rays are not pevatrons, they're indicators of the pevatrons in surroundings. Now, just to show the potential of Lhasa, I said that Lhasa has a, Lhasa has a nice potential for the, yes. So this is the famous source called Cygnus bubble. Actually, Lhasa into the bubble that was Cygnus X source, which is the huge conglomerate of the many star-forming regions. And we also detected the size at least 6 degrees, and just show your spectrum, the spectrum. This point is more than 1 TeV, is almost 2 TeV, PV, sorry, 2 times 10 to 15 eV. For us, it was a dream to get several tens of TeV before, to PV. And the interesting thing in this plot is not the energy. We simply also can measure the direction of this database with accuracy, let's say 0.25 degree. But then there's no other amount from this source because it's very high. And these are about 400 TeV, 600 TeV. So here are more than 40 events of individual gamma rays localized within this Cygnus region. So you just see what is the power. You could see PV sources and the photons that are distributed over this. But there are some coming from the very core, which is history because in the core we have several very exciting sources, including Cygnus X-ray, for example. But it's it works. No. Do I continue? Loud. No. Okay, so it works? I don't think so. Astrophysics appreciate that also. Even it has a very nice performance, very good sensitivity, correct independence, what I mean correct, show not just explain, but essentially getting better and better with energy. That's extremely important because fluxes are getting smaller, smaller with energy. That is the reason the also can get this homogeneous point. You see, even up to 100 PV, we don't see error bars. So that was, it was sensitivity. Okay, let me show you the sensitivity. Once more, you see sensitivity is very the instrument are quite limited. So that's okay. So okay, let's keep this because this is a GRB detection. It doesn't have a direct relation to my topic because gamma rays have been detected here up to 20 TV and instruments called WCDA, Cherenkov telescopes. So that is a bit, it's not simply Lhasa is here. It's just also this amazing event of GRB, which was so strong. It was 60,000 events. But in fact, if you would have the site of Lhasa Cherenkov instrument, which could switch on the source within even 2 minutes, number of events, 60,000 events for 3,000 seconds. This is amazing, right? So it's about more than 20 events per second. You could measure spectrum every 10 seconds. But if you had a Cherenkov telescope here, it could be even 6 million. So that is an interesting point you have to keep in mind. I mean, with having the Cherenkov telescopes combined with this Lhasa detector. This was a really great luck for Lhasa, but it was not my point. So I just want to say about Lhasa, typically we say it's most of us or most of cosmic ray physicists relate this Lhasa result to cosmic rays, saying, oh, finally we solved the so-called origin of cosmic rays around the knee, which is here. Let's, I think, have a better figure. Yeah. So it's, if you multiply to spectrum of cosmic rays 2.7, it's E minus 2.7. You see the flat part here is a knee, and then flux gets down. And often we say, oh, we don't know the origin of the cosmic rays is exaggeration after this 100 years of discovery. We know a lot of them, but of course there are challenges. One of the challenges to understand which sources contribute to this part and how the physics of these sources. Now, as I started saying, that is, we should not exaggerate this question of the contributors to the cosmic rays. It could be by chance, could be just explosion close to us, then cosmic ray flux could be 10 times more. It's local fog. I mean, what we see, it doesn't mean that all science will be reduced, which sources contribute to the knee. It's much more beyond, and that beyond means that, interestingly, I mean, we often do modeling, invoke just extraordinary conditions very often. But in this case, based only on the very basics, classical electrodynamics and ideal hydrodynamics, magnetohydrodynamics, you can get this 1 PV particles just at the margin of possibility from theoretical point of view. So that is much more exciting thing, not just simply which sources contribute to the observed cosmic rays. And Lhasa is going to, Lhasa already put questions, but Lhasa detected PV photons from the Crab Nebula, which are electrons. So if proton pevatron is a challenge, then electron pevatron is almost impossible. But we do see that they are possible. Right? So we have to find a way. So this is a question not only simply astrophysics, it's fundamental physics, how to do all these things. So, okay, let me just go just a bit simpler things. So I'll start saying there's some 20, 30 years ago, starting 70 years ago from Zwicky and Bade, nice paper was they predicted or they claimed that the supernova remnants, actually they didn't say supernova, it says supernovae, but also later supernova remnants are only sources which could be responsible for galactic cosmic rays. So that was believed for many years, and then arrived a very nice theory, diffusive shock acceleration, which is a kind of more sophisticated way of the so-called Fermi one mechanism of acceleration. And then everyone is happy with that the supernova remnants theoretically can explain this. However, there are theoretical doubts. If you go a bit deeper to the problem, you could see it's not so easy to go 1 PV. They have to stop at least 10 TV or 100 TV. That was famous paper by Katrin Cesarsky and Lagash. But that was ignored somehow. There are some people try to find a way how to theoretically do that. They found, in fact, but now our observations, we see gamma rays, the spectrum of gamma rays, this is the spectrum, and these gamma rays are coming from the shell. So all we are happy, but if you look, there's a cutoff above 10 TeV. So it means should be the cutoff in the spectrum above 100 TeV. It's great, but still we are not satisfied because we'd like to have spectrum continuing to 1 PV, this so-called the need. There are some other problems in the source, not still clear. It is electronic source, hadronic, maybe that is used by electrons. But even if you assume this is a hadronic source, we should accept that should be some break or the cutoff. So should be we are unhappy with that or not? Let me skip also this. This is a very interesting point. Just saying that electrons at least are accelerated to 100 TeVs in the source. We see that from the variability of X-rays from Chandra in a very, very small scale, sub-arcsecond scale. We could see variability implying that electrons it can be accelerated, are accelerated up to 100 or more TeV. So that is clear they are electrons. Now, what about the protons? And so I said there's a bit kind of disappointment that we see the cutoff around 100 TeV from RG 7013 from these young supernova remnants. But then appeared that all of supernova remnants, all best candidates, young supernova. Young means less than 1,000 years. Younger, when we have this, they are shock speeds exceeds 2,000 kilometers per second. And if you assume bond diffusion, if you assume something else, amplification of magnetic field, at the end, we could end up with 1 PV, and we are happy with that. Now, theoretically difficult, but we can do that. Now we see all the steep spectra, and then that was even more disappointment. So what? Supernova remnants are not responsible for that. I should say that is very early to make this statement, as many like, because steep spectrum still could be above 100 TeV and could be still effective acceleration. There are ways to get steep spectra, so we should not exclude this possibility. But the question is, experimentally, how we do that. If you want to prove that these young supernova range operate like pevatrons, you have to detect PV, 100 TeV gamma rays. It's extremely difficult because they are quite steep. So here, even in this some CTA white books, you could see that CTA will come and detect pevatrons from Passé. It's a bit naive because look, this is extrapolation, a Powell extrapolation, if I assume not even exponential cutoff. And here's the state of CTA. This is not so, it's almost impossible. Of course, you have to limit your wish about maybe 100 TeV, but certainly not to about 1 going. So this is very difficult task. And Lhasa can do that, but even Lhasa, with such a powerful instrument and sensitivity still needs maybe 10 years to finally say yes or no. Now there are preliminary results to say no, but this is still not sufficient. Now, so should we close this idea of supernova remnants? Again, probably not, because there are a lot of, the Lhasa angular resolution is not great. But even with that angular resolution, you see a lot of middle-aged supernova remnants, some 10,000, 20,000-year-old supernova remnants like W44, W28, similar sources, Gamma Cygni, interacting with the clouds. So there's a basic, very basic way to get gamma rays from these sources. Is a smoking gun. Supernova remnant is old, doesn't anymore produce gamma rays, sorry, particles. But with these particles, when escape, they propagate, and when they one way to get the dense gas clouds, like the red giant molecular clouds, then they could, these clouds could produce gamma rays. Accelerator is there. Your cloud is far from the accelerator, 100 parsec, but that is indicator of the source which was in the past. So that was, and Lhasa has many of this kind. Okay, there are possibly nebulae, they are this kind of sources, they are something else. So we could not claim that exactly are coming. So we need better morphology. That was CTA could do that. Not certainly 400 TV, but maybe 30, 40 PV. And before even Astrid. Astrid could be a great help in this aspect. So now let me just move to stellar clusters. That was not a big surprise, but it was predicted years ago that maybe stellar clusters are better objects to accelerate particles to highest energies than supernova remnants, simply because they have the wind speeds 2,000 kilometers per second. They are inside a more turbulent medium, larger magnetic field, and finally interacting winds. So there are several options, several possibilities to accelerate particles in stellar clusters, young stellar clusters. And then we see now the gamma rays. So the picture I showed you, the Cygni, this one I showed that this is most likely comes from the particle accelerated in there's OB2 stellar cluster is not very powerful. And the most very powerful one, the most powerful stellar cluster actually, young stellar, massive stellar cluster, is so-called Westerlund 1, which is discovered actually 20 years ago. And that also shows it does go beyond 100 TeV closer because the Hess has not such a potential, but we see that also is going to highest energy. So what could be the outcome? I mean, could the outcome very interesting? Maybe not supernova, but stellar clusters. So that is really very exciting. Only do we have sufficient number of stellar clusters young to provide this cosmic ray flux? This is another issue. Maybe yes, maybe not. So we need more detected clusters to do this arithmetics. But yes, another very interesting, exciting issues. Yeah. Oh, okay. So exciting thing is here is that you don't expect, there's not much gas around in this area. I mean, there's maybe one, maybe few cubic centimeter. That's important to get gamma rays, right? But if you take the cosmic ray maximum possible injection protons, acceleration rate like 1038 per second, you cannot get these fluxes unless you assume that particles escape much slower than they would do if the diffusion coefficient similar like we see in stellar medium. So it means to be smaller diffusion coefficient, and in fact that implies very slow diffusion. So this is not a big surprise, but it's unexpected because 2 orders of magnitude slower diffusion than interstellar medium. But this is a thing which there's no way, because we know the maximum luminosity of these objects, so maybe factor of 10 we could reduce, but certainly should be very slow diffusion. One may ask, well, so why should the diffusion slower? Who knows? Maybe because of the cosmic ray could create more turbulence, could increase magnetic field, but also the a priori conditions could be higher turbulence. So that is very new result, and that it will take time to think about all of these things and then to find out. But phenomenologically, it's clear there is a very slow diffusion. And that could be very interesting because then you could have some, like Swiss cheese. I mean, there are just these holes, I mean, but not the holes, so they are accelerated. So particles don't move so quickly and don't feel homogeneously the intestine. But there are sometime, like 10 to 4, 10 to 5 years, they are still surround the accelerators. And then later they just escape until stellar medium. This could have a dramatic impact on the understanding of the secondaries of cosmic rays, anti-protons, etc. So this is another thing which also brings to the unexpected field diffusion, which cosmic rays. Okay, so And then if you now look at the diffuse gamma ray, LHAASO detector also diffuse emission of galactic plane. And in both cases, fluxes are much higher than we would expect if you use the cosmic ray detected, I mean, in local cosmic ray fluxes. So that could mean that they contributed for these concentrations, I mean, of sources surrounding. Again, everything is new. What I'm saying is not stupid. It's possible, but should be still approved all these possibilities. We need some time to understand. But I just want to say what kind of interesting impact would come from this at first glance. Now, well, talking so far one PV, but after the mean spectrum goes about at least 100 TeV, astronomers, cosmic ray physicists believe that it also is galactic. I was taking how it's difficult to have with one PV. Now we certainly have 10 PV accelerator, these signals, and some more now. And then, so what is that? What source? Certainly, signal range hardly can do that. Stellar clusters, I said, I mean, we have to see still, but looks like should be many of them, but we don't see many of them still. It could be because of sensitivity or loud size. Pulsar, I mean, I put here pulsar, how it works. I mean, the model. I mean, you have a kinetic energy moving with subrelativistic speed, or very fast speed, terminates, and at the termination, part of energy of kinetic energy converted to magnetic field. This is a so-called termination scenario. In galactic, in pulsars, it works in a way if you ignore the energy, if you ignore energy of the energy losses of electrons, then you see if you put 10 to 40 erg per second in the kinetic energy, you could get 200 eV. So can we put 10 to 40? Not pulsars. Crab is 10 to 39, but the others less. Now, what could be else there? And the electrons are not so good. They are energy losses. And we know the winds consist of electron-positron pairs. But with our understanding of that. So now I want to show this the crab. Yes, it's very exciting, but there's no time just to say that crab also detected PV photons. Despite all these things, I'm telling you how it's difficult to get them. So, but this is another issue. I just want to move. Binary systems are okay. There are very different type of binary systems. I just moved to the most exciting result, connect to binary system, microquasars. So a few years ago, Vogue published gamma rays, 20 TeV gamma rays, just one point from famous SS433. And that was clear that should be expression of photons or electrons. Later, actually, this is half year ago or 1 year ago, has published paper on with a nice morphology, has a good resolution from SS433. They found the two lobes, and energy-dependent morphology tells us that most likely we deal with the inverse Compton component. And then Hawke published, actually is published or is accepted in Nature, this paper. There's a microquasar called VV4641, and there's a very extended structure around this microquasar. Actually, this microblazar, it has a Lorentz factor of the jet superluminal source, about 10, 9. And now I'm coming to the end of my talk. So as I said, only today or yesterday was in archive. It's submitted to Nature paper by LHAASO. So LHAASO has several sources. It was announced last week in a seminar, but now is also in archive. And so SS433 first. What is interesting, LHAASO, in previous case, there's nothing in the central part house. LHAASO sees from the central mist around SS433 binary system, more than 100 TeV. And interestingly, these are these 3 points. There are no low energies, but this is It's this one. And then from the lobes, you see the low energies. This is from the lobes. So significance, you see very high. They are connected or not. Most likely the central source is hadronic because it correlates with CO observations, gas observations. Sorry, I don't remember CO or H1, but there's a correlation. And then, okay, that is great. That is proof that it could be actually to highest energies because the kinetic energy, as I mentioned before, it's source. But what is the surprise? Then 4 more sources extended, at least 2, surrounding famous objects. One is, you remember I mentioned the Hawk result, 4641 is spectrum is, this guy is here. Look, it goes to 800 TV spectrum. And that means certainly is a super pivotron. And you see the very high threshold is here. There are no points. Low energy is the problem. It's just it's source in southern hemisphere. So it was difficult to, so it's looking at very large zenith angles and then threshold goes up. Another famous source, even more famous, is JAROS 1915. It's extended source. Spectrum is here. Goes beyond 100 TV up to 300 TV. Cygnus X1, probably most famous one. Unfortunately, its significance is only for sigma. After many debates, we decided, okay, we'll see what happens. Not just this is the, we just mentioned for sigma that it's, believe it or not, that sigma is there. In fact, it's higher, but there are some background sources after removal of the source it gets for. And this was, it's funny, this source was included in the paper last week. The paper was prepared maybe 1 year because, I mean, there are just list of potential sources. Now we know multiple quasars could produce this kind of sources. Potential sources, black hole systems. And then when we look this, I mean, they found immediately more than 6 sigma, around 6 sigma. And just last minute, just within 3 days, included in the paper in just in spectrum image. So this is what we have. We have something very interesting situation. I mean, it could be, okay, just go to the summary. If will be question, I could answer because now we would like to detect even more PV, maybe 5 PV, 10 PV photons. It will be very difficult because the flux is even. But there are some of the ways you are interested. I could comment on that. So the Lhasa results we reported so far tell us that is actually the iceberg. I mean, this microquasars arrived recently, so we don't know tomorrow what will come still. Lhasa continues to surprise us with these results. But it's clear that everywhere in the Milky Way we see PV phenomena. So there are PV accelerators, and then Lhasa is a great instrument, but Lhasa has this. It's first of all limit angular resolution. It's not so bad if you have big source, but if you are talking about half-degree sources, or even less, then angular resolution is not sufficient to definite conclusions. So this could be covered by Cherenkov telescopes. And I don't know when happens the CTA, but ASTRI certainly is coming. And ASTRI is exactly in this energy band. I mean, it should not be named that ASTRI will detect hundreds of TV gamma rays because limited observation time, but does matter if you do that even at 50 TV to 100 TV, then you could get, and then you could start to understand, I mean, all the sources, everything is happening. Morphology is extremely important. Meanwhile, the Lhasa will continue observations, and that will more statistics. And of course, we'll see how it looks like this spectra, some features. And one cannot exclude that at the end, I mean, maybe too early, that we maybe this highest energy phenomena, PV and BVONT, are coming from microquasars, not from supernova remnants. That is a bit very revolutionary, but it looks like we are close to that because 100 years, 70 years, we believe that about supernova remnant or supernovae, but it could be microquasars. And very naively, that is okay because microquasars, most of them are ultraluminous X-ray sources. Now we know the kinetic energy luminosity there could exceed 10 to 39 per second, maybe 10 to 40, like SS443, and most likely also Cygnus X-ray. So these are very powerful sources. Powerful, first, all we know. Powerful is good because the flux gamma ray will be higher. But here's situation even more important, more interesting. How maximum energy depends on the power. And these guys are most powerful sources, even more powerful than pulsars. And pulsars, well, there's an exception, scrap, but others are 10 to 37 per second, plus they are electron sources. And microquasar should be hadronic. At least in SS443, we have the jet 0.26 from it is hadronic jet from the ferron line shift. So that we expect a lot of exciting things in near future. Still is not this saturated, this lasso results. So, okay, thank you.
Thank you for the talk. My question was, what is the interpretation for the detection of the gamma emission from the black hole X-ray binaries? Is the jet activity or is the jet interaction with the ISM around the system?
Some of them, this is what and we see this low is net race, it's site of termination of the jet. So that is clear. Others, like GRS 1915, it also has a jet, but they have also wings. And since the maximum energy is in the wind kinetic energy, and these are extended sources. So it could be most likely wind rather than jet. But then it's not clear. Maybe you don't see the jet. So this UV4641, in fact, the jet is very unusual. It is more than, I think it's 9 or 10 Lorentz factor. It's like blazars. And so a lot of things we don't know. We only recently, like half a year ago, we learned that Cygnus X-ray has a wing, and the kinetic energy in the window of Cygnus X-ray is 5 times 10 to the 9. We didn't know about that before, what this polarization measurement we expect. So extended sources, most likely, they are accelerated not in the binary system, but well, probably could both accelerate inside. I mean, so there, go and energize the medium surrounding. So it's very new. I am not, I cannot just from phenological point of view, these are very high energies, and we need the power. And these guys do have this power. Now, how it works? Maybe this scenario is termination of the wind, and later you produce shock accelerated particles. So that could be most likely scenario. We could not exclude, like for example, Cygnus X. We don't know yet. Maybe some others could be variable, but that means that everything is produced close to the binary system or inside the binary system. That could be very important to have such evidence because that will mean also to be not in only one place, especially from places. So yes, at the first, if you look data, they are a bit disturbing, high fluxes, but not crazy. Not crazy. It is possible with such a power, but what are details? I think we'll see. It is, I think, too early now just to, but I think things are developing so fast also. I'm sure soon will appear many models, maybe 90% wrong, but maybe some 1 or 10 will be right. So it is going on. And this is public, so
Thank you.
I was planning to, we decided last week to announce it. This it doesn't matter. The state, because these extended ones are coming from the termination of kinetic energy. You could have they should not necessarily connect with each other. I mean, you could have high state means X-rays. So it could be high state, low state, acceleration, local acceleration inside the, but what is important is, well, if not stationary, but quasi-stationary wind with the power. So in extended sources, it really doesn't matter. It's you need the average kinetic energy. If we don't have still evidence that it comes from, is variable, then you could study correlation with gamma rays, X-rays, gamma rays, I mean, low energy gamma rays. So that for the future, some interesting results are coming. I cannot tell you that, but in that case, we could talk about this correlation. And as I said, how long the integration time? Integration time is just what is for 3 full years, 3 or 4 full years. With Lasso, previously Lasso started to take data, even it was completed only 25%, and half, and then 75%. This was continuously taking data, but the results are coming last 3, 4 years. And so it's integrated during the time. There is a analysis. I mean, if you have extended source, you don't need to spend your time on trying to find the variability. But if you don't know it's extended or not, then that makes sense to look at the variability. Since the resolution does allow you to judge, this is the point-like source extended. And but the significance, you see 6 sigma maybe is not sufficient. I mean, if you collect for 4 years, one cannot exclude that you have 2 sigma flares during this time. I mean, but and altogether will give you 6 sigma, but it's not sufficient. Probably we need to have, and that cannot happen if you observe 3 years. Again, you could have the same. But if you are likely to have the very strong flare, then that could be interesting. That could be interesting to look at them. So Lhasa is a large field of view. All these microquasars are in the field of view. So if something happens, then we'll see.
So LASO see the microquasar as persistent sources, isn't it?
These always.
Okay. Yeah.
As I said, extended one is by definition should be persistent source, right? Cannot be variable. But sigma 6.1 and I think the size is comparable with the PSA. So
Okay.
it's
Because
difficult to say.
the Maxi one, I think it's a transient source. I think.
It could be. No, actually, honestly, I didn't know about that source myself, but that was a transient source. Yes, now I know this transient source. But as I said, it doesn't matter. A transient means just X-rays are going for some internal processes are going. But the total energy is sitting in the wind. And it, of course, wind also could be maybe, but doesn't matter. I mean, the average rate of injecting energy into the medium.